My presentation shows the development of a tool that enables planners at Metro in DC to forecast the impact of similar policies, including things like fare capping, into the future. So some introductions are in order. My name is Ehab Ebeid, like Kevin said. I'm a transportation planner and data scientist at Foursquare ITP. But this project wasn't solely my work at all. It's actually a huge team effort. So I want to first recognize the project team. The project was led at the WMATA side by Gabe Pincus and Sydney Goldstein, with involvement of many, many others. The project also involved many team members at Cambridge Systematics, including, off the top of my head, Scott Boone, Andrew Kay, Dan Patterson, Shrikant Flurari, Alex Rubin, Given Demyati, and many others. And at the Foursquare ITP side, the team members included Wiley Timmerman and myself. So some background is that decision makers and transit agencies face a lot of pressures from different sides when making decisions regarding fares and fare structures. And they also face a lot of uncertainty in reckoning with the impact of such fares changes on ridership, revenue, and fare subsidy. And WMATA in particular has a relatively complex fare structure, especially for Metro Rail, which can make it difficult to calculate such things like the expected revenue changes from fare products, or what decisions regarding fare products riders would make when changes are made to these products. And more importantly, increasingly importantly, we think about the distributional impacts of these impacts. So the impacts on ridership and subsidy and revenue are socially stratified along stratifiers like race and class. So WMATA Metro Rail services have a relatively complex fare structure, since fares are unique to each station pair dependent on distance. Customers may purchase many different types of passes that are more expensive than they need potentially, like Abu Bakr mentioned in the previous presentation. And there are also a variety of discounts that are available based on transfer behavior and some rider characteristics. So this is a relatively complex fare system. The other thing is that the kind of opportunity here also is that agencies increasingly have a wealth of data sets, including automated fare collection data sets, automated vehicle location, and automated passenger counters, or AFC, AVL, and APC respectively. But there are a lot of challenges in using them, how to effectively use them for planning and decision making in agencies. Some background specifically about how fare modeling has been done before at WMATA. So there was an earlier tool for fare modeling based in Excel. It relied on onboard fare surveys as the main data source, but was relatively limited, and as I mentioned before, did not include the wealth of data from automated sources that we have access to today. And so a subsequent iteration was built in Tableau with the main data sources still including the onboard fare survey, ridership survey, but also including some an origin destination inference model called Trace, which I'll refer to later in the presentation, which is basically using some logical rules and rules for inference, integrates data from automatic fare collection systems and automatic vehicle location, automatic passenger counter systems to come up with a picture, a more complete picture about what each transit ride means and what it does exactly in the system. However, there were challenges with specific types of complex fare modeling questions and flexibility and configuration in this in the Tableau model that was later built. And so we sought to replace it with a more kind of computationally flexible product. So the new tool also uses some of the same main data sources, onboard surveys, Trace, and others. It offers a wider range of fare scenario configurability and many additional analytic capabilities that I'll touch on later. It is based in Python and SQL, And one of its kind of user interfaces, there's a command line user interface, but there's also a graphical user interface in the form of a web application, a screenshot of which you can see right now. So the model components is that it basically takes this trace data, which is the origin, destination, transfer, inference model, combines it with the onboard survey data, and combines it also with a lot of data in the system about the rail system, the rail structure, the network. And then there are several pre-processing steps in which surveys are synthesized um, in order to join them to automatic fare collection data points. And we also transform the trace data set. So by basically making ride trip level information wider, including many more columns about them. That's then combined together into a data set that we call base ridership, which is itself incredibly useful for analysis in the agency going forward. And then later on, all of these data sources are combined into three main uh, outputs of this fare and service model. The first one is a card level fare modeling output, which mostly deals with monthly type passes, making helping the planners make decisions or understand what the impact of their decisions would be on who would take up a new fare product, a monthly fare product, as well as some other kind of more traditional service fare and service model outputs, like walk-up fare modeling and a rail service elasticity. So this tool can be used in a variety of ways. It can answer business decisions such as how did the travel market change between two periods of time? This is kind of related to comparing this base ridership um, uh, output and then applying to it to two different, capturing a base ridership output from two different time points and then comparing them. Questions like what are the impacts of fare changes on ridership, revenue, and subsidy? And then importantly, how are these impacts experienced differently across different demographic groups? Finally, we also, kind of more specifically, planners often wonder um, what is exactly the point of diminishing returns when fare increases could result in decreased ridership? And we can answer this question here with real data sets based on agency-specific fare elasticities, but also agency actual trips taken on the agency and documented using automatic data sources. The kind of inputs and outputs for this model enable the users to select a period of time to analyze, select variables to include, like minority status, low income status, jurisdiction. WMATA operates in multiple, and customer segmentation, which comes from a previous project that segments customers based on their travel patterns. It enables users to use this ridership data for any purpose, not just for as an input to fare modeling, and also to define two separate fare scenarios before and after, and apply those scenarios to the same ridership data set to understand what the difference would be between the two different scenarios. Um, and the types of calculations that are made possible are to determine the change in cost per journey for each unique trip type identified by the origin, destination, and also the time of day, for example, and the specific service day, to apply an elasticity based on trip length and mode to this change between the two scenarios, and to calculate the change in ridership and revenue as a result of this change. This is a short walkthrough of how the tool works. We first establish a database connection and then set up this base ridership query, which is basically a query into the database of uh, ridership and that integrates together the origin destination inference model with onboard surveys. So these basically these are the types of attributes that the user can set, including some demographic attributes here, and political attributes in the case of home jurisdiction, what types of operators the user is interested in, the period, of course, and maybe even naming the scenario for use later in comparison. Um, then here we have the option of kind of comparing before and after, configuring the scenarios to set up a before and after scenario. And since this is also a service model, we have a lot of configurations here that can be provided as a CSV to give more information about what service changes are underlying the network, so before and after. So it's not just a fair model. So the output for fare modeling specifically gives both ridership in both the baseline and the proposed scenarios, the revenue in the baseline and the proposed scenarios, and also provides a lot of different fields for aggregation, specifically things like day type, fare period, and demographic attributes. So this screenshot here shows you that the types of comparisons that you can make when kind of choosing the aggregation to be low income status, and then seeing the types of both ridership and revenue changes according to comparing across low income status. So this is it for me. Yeah, I'd like to thank the project team and you all for listening, and we can open it up for questions from the moderators. Thank you so much.